Alright everybody, in this video I'd like to talk to you all a little bit about how to balance and later on how to write and balance chemical equations. We're going to start off here with 4 pre-written chemical equations that we're going to balance. And then after that we're going to take some sentences that describe chemical reactions, and these are a little bit more difficult. Write out the chemical reaction that corresponds to whatever is written here and then balance it. So let's start off with balancing first. There's a couple of rules that we want to go by. And if we just, let's say, use these 4 reactions as an example, notice there are certain elements that appear virtually every time. Those are oxygen, 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 hydrogen, hydrogen, hydrogen. Okay, hydrogen's not up there. The fact is, hydrogen and oxygen appear in pretty much every chemical reaction. So because they're so prevalent, and because they usually exist in more than one species on each side of the equation, it's best to leave those until the end. For example, you've got oxygen in water, you've got oxygen in CO2. Trying to balance the oxygen here to get it to balance both of these before you do anything else is extremely complicated. Alright, so the first rule is you always want to balance whatever is not involved with hydrogen or oxygen. So that's usually metals, things like that, metals, or perhaps sulfur, cobalt, for example, calcium. The elements that you, or the species that you can balance last, are always the ones that are by themselves, because if the carbon's by itself here and you balance everything and figure out, well, I need a certain number of carbons, well, because it's by itself, you can just add whatever number you want to there, and that makes it kind of nice. The same for oxygen by itself. You'll see that when we balance this reaction along with this one, what we balance at the end is the carbon and the oxygen, because it's easiest to do it that way because those are by themselves. All right. Okay, and you can see these reactions appear to get more complicated the further we go down here. We're not concerned about at this point you being able to predict what these products are going to be. That's not the focus at all. The focus is, if we write this reaction out for you, can you balance it? Okay. Alright, so let's start up at the top here. We have copper 1 oxide plus carbon giving metallic copper and carbon dioxide, carbon monoxide, I'm sorry. So the simplest thing to say here is we're going to leave the oxygen till the end. And let's see, what else can we balance? Well, it actually looks like everything is balanced apart from the copper. 2 coppers, 1 copper. So if I just put a 2 here, 2 coppers, 1 oxygen, 1 oxygen, 1 carbon, 1 carbon. So that's actually a very, very simple example of balancing an equation. Let's go down to this one, because this one's considerably more involved. The oxygen and hydrogen, like we said before, we're going to leave till the end. And because the oxygen is on its own, we're going to leave that right till the end, so the order of balancing is going to be carbon, hydrogen, then oxygen. So let's do the carbons first. We've got 3 carbons. This is something called propane. Some of you may have big tanks of it outside your house that are used to heat your house. Propane, 3 carbons. The only place I have carbon here is in the CO2, and I only have 1 carbon there, so I'm going to put 3 as the coefficient there to balance out my carbons. Next, we're going to do the hydrogens. Well, that's 8 hydrogens here. The only place I have hydrogens here is in water, and there's 2. So how many times does 2 go into 8? Well, of course, that's 4 times. So now I've balanced for my carbons, I've balanced for my hydrogens. All I have to do now is balance for my oxygens. And so the simplest way to do that here is just to say, well, I've got 4 oxygens on this side. I've got not 3 oxygens here, but 6 oxygens here, because you remember each CO2 has 2 oxygens, so therefore that's 6, for a total of 10 oxygen atoms. In one oxygen molecule, there are 2 oxygen atoms, therefore I'm going to need a total of 5 of these, not 10. All right. So 6 oxygens, 10 oxygens, 10 oxygens. So everything is balanced. All right. So let's go down to the next one. When we have species that contain polyatomic ions, like silicate here and bicarbonate, the first thing we want to ask ourselves is, well, are the polyatomic ions the same on each side? Because if they are, you can just keep them the way they are. There's no need to break everything up. Of course, you can see that we have silicate here, but we don't have silicate on the other side. We have bicarbonate here, but we don't have bicarbonate here, so that means we have to break everything up. Now remember what we said before, let's leave the hydrogen till the end, let's leave the oxygen till the end. Let's look at the calcium and the silicon first. So you can see we've got calcium, one calcium, alright? We've got one silicon. This is looking pretty simple so far. Let's look at the carbons next, alright? We've got one carbon on the left. Now how many carbons do we have on the right? Well, we've got two bicarbonates, each bicarbonate having one carbon, so therefore we've got two carbons here. We don't have two here, so therefore we need a coefficient of 2. All right. Oxygen is present in every single molecule here, so we're going to leave that right till the end. Hydrogen's only present in one molecule here and one molecule here. How many hydrogens do we have in this molecule? Well, it's the same as for the carbons. We only have 2. We already have 2 hydrogens here, so we're all set. Now, let's be careful and add up all the oxygens. All right, how many oxygens do we have here? We have 2 there. We have 3 per bicarbonate, but we have 2 bicarbonates, so therefore we've got a total of 6. So therefore, in total on that side, we have 8 oxygens. And what do we have here? Here we've got 1. Here we've got 3. And here we have 2, but there's 2 of those, so we have 4. 4 plus 7 plus 8. What do you know? We have 8 oxygens on each side, so that's balanced. Now let's go down to this one. Look at the polyatomics. Nitrate. Oh, what do you know? Nitrate. Ammonium. Ammonium. So the polyatomic ions are both present on each side, so we don't need to split them up. Oh, sorry about that. We don't need to split them up. We just need to make sure we have equal numbers of each polyatomic ion on each side. All right. But we're going to do the same thing as we did before. We're going to balance everything other than what contains oxygen and hydrogen. So let's forget about the ammonium and the nitrate for now. Let's balance the cobalt and the sulfur. And this is not all that difficult. And you know what, hang on a minute. Let me just make one change here. I messed up a little bit. This should be cobalt 3 nitrate. That should be a 3. If I have 3 sulfurs here and I have 1 here, you can imagine I need a 3 here. Now that means 3 sulfurs, but also 3 of these as well. Or 2 of these, I should say. Cobalt we have 2, here we have 1, so therefore we need that 2. So we've balanced for our cobalt and our sulfur. Now we've got to balance for the ammonium and the nitrate. And because these are together in this molecule and they're in a ratio of 1 to 1, we should be able to say that we have equal numbers of each here. So let's see how many nitrates we have. Well, for every molecule of cobalt 3 nitrate we have 3 nitrates. But we have 2 of those, so in total we have 6 nitrates. And for the ammonium, for every molecule of ammonium sulfide, we have 2 ammonium ions, but we have 3 of those, so that gives us a total of 6 ammonium ions. So therefore, it's not too much of a stretch to see we balance that by putting a 6 right there. And that is the basics of how we balance chemical equations. So let's go one step further. What if we had a situation like this, where we didn't have a chemical equation at all, and we had to actually figure out what the equation is before we can even think about balancing it? This goes back to our naming business that you saw in the last chapter or earlier on in this chapter, for how you actually go from a name to a structure. Let's start here. Iron oxide. So obviously that contains iron and oxygen. Now, what does that 3 mean? Who remembers what the 3 means? Well, the 3, the only time you're going to see this 3 in brackets here in Roman numerals is when you're dealing with a transition metal. And what that tells you is the charge on the iron is Fe3+. The oxygen in this form of oxide always forms the same charge. You remember oxygen is in group 6 of the periodic table. every element when it reacts is trying to gain its outer shell of 8 electrons. If oxygen's got 6, it needs 2 more. So the oxide ion is O2 minus. So how do these two add together to give you something neutral? Well, we have to think about what's the smallest number that both of these can go into? Well, the smallest number is 6. 3 can go into 6 twice. 2 can go into 6 3 times. And that is where that comes from. I would not recommend that you just cross multiply, because in some cases that doesn't work. Alright? In a lot of cases it does. You just have to be a little bit careful with doing that cross multiplication in some cases. Alright? Alright, so that's the iron oxide. And it says hydrogen gas. So does that mean hydrogen gas? Well, we have the state right, but hydrogen doesn't exist as a gas as far as atoms go. Hydrogen gas is a molecule of hydrogen, which is H2. Those react to form solid iron, so in other words, just iron by itself, and liquid water. Now, I don't think we need to worry about the formula for water, at least I hope not. Alright, now, we have everything done, so let's balance. Remember what we said before? Leave the oxygen and hydrogen till the end, so let's balance the iron first. So we've got to have a 2 right there. The hydrogen is by itself, so we're going to leave that right to the end. So now we're going to do the oxygen. 3 oxygens here, only 1 here, 3 H2O. Therefore, 3 H2O here, meaning 6 hydrogens. We have 2 here, so we multiply that by 3. Let's check. 2 ions, 2 ions. 3 oxygens, 3 oxygens. 6 hydrogens, 6 hydrogens. Bingo, we're done. Next one. Ammonia. In some cases, the question will give you the formula of a molecule because you may not necessarily know it. Ammonia, but gaseous ammonia, so NH3 gas, reacts with gaseous oxygen to form gaseous nitrogen monoxide. Now this is a naming issue again. Nitrogen monoxide, mono meaning 1, so there's 1 oxygen. If there's nothing in front of the nitrogen, it means there's 1 nitrogen as well, so therefore NO plus H2O gas. Anybody who's listening to this video own a cat? Or not own a cat, have a cat live with you? If you do, as we do, one thing you'll know, particularly if it's an indoor cat, one of the less pleasant things about owning an indoor cat is that you've got to change the litter tray. And I'll be honest, sometimes I don't change it as often as I should. And I go in there and we have our litter tray in our the utility room where we do the washing and stuff. And sometimes it's a bit stinky in there, and it's always a very particular sharp, pungent smell. And that's because as the cats pee, mainly the pee, as it decomposes, it gives off ammonia. Alright? That's what accounts for the strong, sharp, nasty smell when you walk in there if you haven't cleaned the litter tray in a couple of months, days. Alright. Alright, let's go ahead and balance this. Oxygen is by itself, so we're going to leave that right till the end. We're going to leave the hydrogen until next. We're going to balance the nitrogen first. So 1 nitrogen, 1 nitrogen. We seem to be okay there. 3 hydrogens, 2 hydrogens. How can I balance that? Well, I don't really want to put a 1.5 here. But how about if I do this? If I say 3 hydrogens and 2 ammonias. Notice that gives me 6 hydrogens and 6 hydrogens. I found the lowest common number that 2 and 3 go into, as we did up here, and put that as the coefficient. Now, bear in mind, of course, by my doing this, I've changed the number of nitrogens here, so I've got to do the same here. Alright? Everybody see what I did there? Didn't change the nitrogen first, but when I changed the hydrogens, it changed the nitrogen as well. You always have to make sure that you stay on top of changes like that. Once we've done that, what we have now is everything balanced apart from the oxygen. So let's just think about this. We have 3 oxygens here. We've got 2 oxygens here, giving us a total of 5 oxygens. Now you'll notice there was no number that goes into, there's no number, or there's no way to get 2 into 5 without using a fraction. So what I could say is, well, I could do this, 5 over 2 oxygens. And people will tell you different things about this, but technically you aren't supposed to have fractions when you're balancing a chemical reaction. If you do, the ratios are still the same, but for completeness, it's probably a good idea to try and get rid of the fractions if you have them. And there's a simple way to get rid of this fraction, 5 over 2. And the simple way is just to multiply everything by 2. Because when you multiply this by 2, you get 5. Multiply this by 2, you get 4. Multiply this by 2, you get 4. Multiply this by 2, and you get 6. Alright? Now, that's the first time that we've done this, so let's actually check that these all add up to what they're supposed to add up to. Alright? So let's see. Nitrogens. We've got 4 nitrogens. We got 4 nitrogens. We got 12 hydrogens. We got 12 hydrogens. Oxygens, we've got 10 oxygens. We've got 4 here, 6 there. Bingo, we're done. That's good. Alright, last one. Then I'll leave you alone for a little while. Sulfur dioxide reacts with oxygen gas to form sulfur trioxide. The key here is sulfur and oxygen in each case, but the prefix is di and tri. Di, of course, meaning 2, tri meaning 3. So therefore, 1 sulfur with 2 oxygens, and that's a gas, reacts with oxygen gas to form sulfur trioxide, tri meaning 3. And that's it. You can already tell this is going to be a much simpler equation to balance because we don't have as many species and we only have 2 different elements there. So let's balance the sulfur first. Well, the sulfurs appear to be balanced, so let's look at the oxygens then. We have 3 oxygens here and 4 oxygens here. So how are we going to do that? The problem that we have here is that we have oxygen in 2 different places. All right. So we're going to do a little bit of trial and error to figure out exactly what the best way to go about this is. All right. All right. Let's just try it this way. If we had 2 of each of these, all right, 2 sulfurs, 4 oxygens, 6 oxygens, and we'd have 6 oxygens here. Notice all I did was I multiplied everything by 2 apart from the oxygen, and that kept my amounts of sulfur the same, but gave me 4 oxygens here, 2 oxygens here, 6 oxygens here. And 4 plus 2 of course is 6, so that means everything's balanced. Alright. Okay. And basically that's how we go through and balance chemical reactions. Alright. If you'd gone through this one and tried to say, well, I'm going to try and put a 2 in front of the O2, you'd find that you'd have 1 too many oxygens on this side. You can just keep on going until you get the right number. It is sometimes a case of trial and error until you get it right. But if you have a situation where you have the 2 elements together and the same 2 elements just in a different ratio, usually you can get by multiplying those 2 by some number and then figuring out what you need to do with whatever is left over. But anyway, that is the basics of balancing and writing chemical reactions. Alright? Thank you.